Hello everyone. In this video, we are going to learn a simple but important topic, planar graphs. We have two parts in the lecture, planar graphs and Euler's formula. A planar graph is a graph that can be drawn on the plane in such a way that its edges only intersect at their endpoints. Euler's formula is to study the relation among the number of vertices, edges, and faces in a planar graph. The first definition is a polygonal path or a polygonal curve. A polygonal path or a polygonal curve in the plane is the union of many line segments such that each segment starts at the end of the previous one and no point appears in more than one segment, except for common endpoints of consecutive segments. Here the graph below is a polygonal path. It consists of 5 segments. Almost every point appears in exactly one segment, except for A2, A3, A4, A5. These 4 points appear twice because they are common endpoints of 2 segments. In a polygonal UV path, the beginning of the first segment is U and the end of the last segment is V. So the graph below is an A1, A6 path. This polygonal path starts from A1, ends at A6. Let's draw another graph. This figure is not a polygonal path because this point appears twice in 2 different segments, but it is not a common endpoint of 2 segments. So here we have 2 examples. The first is a polygonal path. The second is not a polygonal path. The next 2 definitions are planar graph and plane graph. A drawing of a graph is a function that maps each vertex v of vg to a point fv in the plane, and each edge uv to a polygonal fu fv path in the plane. The images of vertices are distinct. Here, the graphs below are complete graphs of order 4. Both of them are K4. Both of them are the drawings of the complete graph K4. We can map the vertex 1 to F1, 2 to F2, 3 to F3, 4 to F4. Such that each edge is mapped to a polygonal path in the plane. A point in FE intersection FE prime other than a common end is a crossing. Here this point is in both the segment 1, 4 and the segment 2, 3, but it is not a common end. So it is a crossing. A graph is planar if it has a drawing without crossings. If it has a drawing without crossings, the graph is called a planar graph. K4 is a planar graph because even it has a crossing in this drawing, it has no crossing in this drawing. So it is a planar graph because it has a drawing without crossings. Such a drawing is a planar embedding of G. A plane graph is a particular drawing of a planar graph in the plane with no crossings. So the first graph with a crossing is a planar graph but not a plane graph. The second graph is a planar embedding and a plane graph. Let's repeat it again. A planar graph is a graph that can be drawn in the plane without crossings. A plane graph is a planar graph that has been drawn in the plane without crossings. So the two graphs below are planar graphs, but only the second one is a plane graph. We have two remarks. The first remark is, even if a graph does not look like it is planar, it may still be drawn without crossings, so it is planar. This graph below has two crossings, two crossings, but it is planar because it can be drawn in such a way that it has no crossing. The second remark is, we get the same class of graphs if we only require images of edges to be continuous curves. Polygonal curves can be replaced by continuous curves. This is because any continuous line can be arbitrarily, accurately, approximately by a polygonal curve. So this is a planar embedding of K4. This is also a planar embedding of K4. We don't care if the edge is a polygonal curve or a continuous curve. Both okay. Here, this edge is not a polygonal curve, but it can be replaced by a polygonal curve. So it's also a plane graph. These three graphs are plane graphs or planar embeddings. The next definition is faces of a plane graph. An open site in the plane is a site U such that for every point P belong to U, all points within some small distance from P belong to U. So here, this is an open site, because for any point P, we can find all points within a small distance belong to U. A region is an open site U that contains a polygonal UV path for every pair UV belong to U. That is, it is path connected. The faces of a plane graph are the maximal regions of the plane that are disjoint from the drawing. So here, in the plane graph below, we have four faces: F1, F2, F3, and F4. We have four faces. Note that F1, F3, F2 are bounded face, but F4 is an unbounded face. F4 is the area outside the graph. Here we have another example, K4. In this drawing, we have 1, 2, 3, 4, 5. We have 5 faces. Is this right? No, it's false. It is not correct. Why? Because when we are talking about faces, we are talking about faces of a plane graph. The first graph is not a plane graph. It has a crossing. In fact, a planar embedding of K4 has 4 faces: F1, F2, F3, F4. Here we have another drawing of K4. It has 4 faces: F1, F2, F3, F4. Now we come to the Jordan curve theorem. For accuracy, we give the theorem here, but we do not prove it. It's not easy to prove. Jordan curve theorem says that a simple closed polygonal curve C consisting of finitely many segments partitions the plane into exactly two faces, each having C as boundary. Like the figure below, this closed polygonal curve is C. It partitions the plane into exactly two faces, each having C as boundary. Here in the left, all the three curves are Jordan curves, but in the right, the three curves are not Jordan curves, because this curve is not a polygonal curve. These two curves are not closed. We need to say that the result is true in two dimensions, in the plane, but this is not true in three dimensions. In R3, there is a surface called the Mobius band, which has only one side. A closed polygonal curve cannot partition the Mobius band into two faces. If you are interested in Mobius band, you can Google it yourself. Another remark is, the faces of a plane graph G are pairwise disjoint. They are separated by the edges of G. 2 points are in the same face if and only if there is a polygonal path between them which does not cross an edge of G. Here we have 2 points. The 2 points are in the same face because we can find a polygonal path between them do not cross any edge of G. Also, note that a finite graph has a single unbounded face. This face is an unbounded face. It's the area outside the graph. Now we have a proposition about a forest. A forest is a disjoint union of trees. So a forest can always be drawn in the plane without crossings. A forest is a planar graph. The proposition says a plane forest has exactly one face. The graph below is a plane forest. We can see that it has only one face, which is unbounded. For any 2 points, we can find a polygonal path joining them. So a plane forest has exactly one face. For a face, it has a definition, length. The length of the face f in a planar embedding of G is the sum of the length of the walks in G that bound it. Let's take an example. Let LFI denote the length of face Fi. The plane graph below has 4 faces, F1 to F4. Let's calculate the length of the faces. For F1, the length of F1 is 1, 2, 3, 4, 5, 6. The length of F1 is 6. Note that the length of a face is not the number of edges incident to the face, but the length of the walk bounded. To calculate the length of F1, this edge is counted twice. Why? Because every edge has 2 sides. As you move around the face, you see both sides of the edge. Every edge has two sides. Both sides should be counted. The length of F2 is 1, 2, 3. The length of F2 is 3. The length of F3 is 1, 2, 3, 4, 5. The length of F3 is 5. Now we calculate the length of F4. The length of F4 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So LF4 equals 14. Note that this edge is counted twice because when we travel around the outer face, we see the bridge edge twice, both sides of it. So it's counted twice. So we need to pay attention that the length of a face is not the number of edges incident to the face. Here is another example. Let's calculate the length of the four faces. This face has 1, 2, 3. The length of this face is 3. The length of this face is 1, 2, 3, 4, 5, 6. The length of this face is 6. The length of this face is 1, 2, 3, 4, 5, 6. It's 6. The length of the outer face is 1, 2, 3, 4, 5, 6, 7. The length of this outer face is 7. Every edge is counted twice because every edge has two sides. The two sides may contribute to one face or two faces. We have a proposition on the length of faces. It says that if LFI denotes the length of a face Fi in a plane graph G, then 2 times EG. EG is the number of edges in the graph G. 2 times the number of edges equals sigma LFI, the total length of all faces. The proof is simple. Because in the sum sigma LFI, every edge was counted twice. We will use this proposition later. Now we come to the second part, Euler's formula. Euler's formula in graph theory was given in 1758. The theorem says that if a connected plane graph G has exactly n vertices, e edges, and f faces, then n minus e plus f equals 2. Note that the prerequisite is G is a connected plane graph. We have 3 graphs below. In the first graph, n equals 1, 2, 3, 4. n equals 4. And the number of edges is 6. 1, 2, 3, 4, 5, 6. And the number of faces is 1, 2, 3, 4. 4. So n minus e plus f equals 4 minus 6 plus 4 equals 2. In the second graph, n equals 8, e equals 12, f equals 6, and n minus e plus f equals 2. In the third graph, n equals 6, e equals 12, f equals 8, n minus e plus f equals 2. It's amazing. So how to prove Euler's formula? We will prove Euler's formula by induction on the number of edges. Now we prove the formula. We use induction on the number of edges in G. Because G is a connected graph, so the number of edges is greater than or equal to n minus 1. If EG equals n minus 1 and G is connected, then G is a tree. We have learned that for a tree or a forest, it has exactly one face, f equals 1, e equals n minus 1. So n minus e plus f equals 2. This is the induction basis. If EG is greater than or equal to n and G is connected, G contains a cycle, C. We can choose any edge G from the cycle C, and let G prime be obtained from G by deleting the edge G. So the new graph G prime and G have the same number of vertices, and the number of edges of G prime is the number of edges of G minus 1, because G prime is obtained from G by deleting exactly one edge G. Then G prime is connected because the deleted edge is from a cycle, and EG prime is greater than or equal to n minus 1. So we can use the inductive hypothesis. By the inductive hypothesis, for G prime, we have n prime minus e prime plus f prime equals 2. Here n prime equals n and e prime equals e minus 1. Also, deleting G unites two faces. G is not a leaf edge, G is not a cut edge. So deleting G unites two faces. So f prime equals f minus 1. So from this formula, we have n minus e minus 1 plus f minus 1 equals 2. So we have n minus e plus f equals 2. This is the whole proof. It's easy. The proof technical is induction on the number of edges. We need to remember this formula, n minus e plus f equals 2, is very useful. We have a remark. The fact that deleting an edge in a cycle decreases the number of faces by 1 can be proved formally using the Jordan curve theorem. From Euler's formula, we have a theorem about the relation between the number of edges and the number of vertices. If G is a simple planar graph with at least 3 vertices, then EG is less than or equal to 3 times G minus 6. The number of edges is bounded by the number of vertices times 3 minus 6. If G is also triangle free, then EG is less than or equal to 2G minus 4. The theorem has two parts. We first prove EG is less than or equal to 3G minus 6. It suffices to consider connected graphs. Otherwise, we can add edges to connect the graph. For example, this is a non-connected graph. To prove the result for this non-connected graph, we can add edge to this graph. To connect the graph. If the result holds for this connected graph, then the result holds for the original graph. because the original graph has less edges, so it suffices to consider only connected graphs. Every face boundary in a simple graph contains at least 3 edges. We know that every face boundary has at least 3 edges. So the length of every face is greater than or equal to 3. Let Fi be the least of face lengths. Each Fi is greater than or equal to 3. Then 2G equals sigma Fi. This has been proved before because every edge is counted twice when calculating the sum of the lengths of the faces. And sigma Fi for I from 1 to f is greater than or equal to 3f. Because there are f faces, the length of each face is at least 3. So sigma Fi is greater than or equal to 3f. So we have 2e greater than or equal to 3f. It implies that f is less than or equal to 2/3 of e. Substitute this into Euler's formula. We have n minus e plus 2/3 of e is greater than or equal to n minus e plus 2/3 of e is greater than or equal to f. So n minus e plus f equals 2. So we have n minus e plus 2/3 of e is greater than or equal to 2. So we have n minus 1/3 of e greater than or equal to 2. That is 3n minus e is greater than or equal to 6, and e is less than or equal to 3n minus 6. So we have the first result. The first result is from 2 ingredients. The first ingredient is Euler's formula, n minus e plus f equals 2. The second ingredient is every face boundary has at least 3 edges. Now we prove the second result. If G is also triangle free, then EG is less than or equal to 2G minus 4. When G is triangle free, the faces have lengths at least 4, except in the case of K2, but G is a simple planar graph with at least 3 vertices. So this exception is avoided. In this case, we have 2G equals sigma Fi, and Fi is not greater than or equal to 3f. Here is greater than or equal to 4 times f, because every face has length at least 4. So we have 2e is greater than or equal to 4f. So e is greater than or equal to 2f. We have n minus e plus a half of e greater than or equal to n minus e plus f, because a half of e is greater than or equal to f. N minus e plus f equals 2. So we have n minus a half of e greater than or equal to 2. That is, e is less than or equal to 2n minus 4. Our proof is done. From the theorem, we have a corollary. We will use this corollary later. If G is a planar bipartite graph with n vertices, n is greater than or equal to 3, then G has at most 2n minus 4 edges. This is a direct corollary because G is a bipartite graph. So G has no triangle. G is triangle free. So EG is less than or equal to 2n minus 4. G has at most 2n minus 4 edges. Now we have the corollary, that is that K5 and K33 are not planar. There are some different proofs for this result. Here we have a proof by using Euler's formula. K5 is a non-planar graph because let's calculate the number of edges of K5. The number of edges of K5 is 10, and the number of vertices of K5 is 5. So 3 times 5 minus 6 equals 9. So we have E is greater than 3n minus 6. But we have learned that for a simple planar graph, E is less than or equal to 3n minus 6. Here E is greater than 3n minus 6, so K5 is a non-planar graph. Also, K33 is a non-planar graph because we can calculate the number of edges. The number of edges of K33 is 9. And the number of vertices of K33 is 6. 2 times 6 minus 4 is 8. So here we have E is greater than 2n minus 4. But we just learned that for a planar bipartite graph, E is less than or equal to 2n minus 4. So K33 is a non-planar graph. The last question is to create a maximal planar graph. Here is a planar graph. If we add one edge to this planar graph, it is still planar, then we add this edge. We can go on adding some edges to make a new graph, and the new graph is still planar. Now we see that we can still add more edges. It's still planar. Can we add some more edges? Yes, we can. It's still planar. Now we cannot add more edges to this graph because if we add one more edge to this graph, it becomes a non-planar graph. Let's check the length of each face. This face has length 1, 2, 3. 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 The outer face has length 1, 2, 3. Every face has length exactly 3. This is a maximal planar graph. A maximal planar graph is a planar graph, but adding one more edge will create a non-planar graph. The final remark is maximal planar graphs and the triangulations are in fact the same. The proof of the theorem shows that having 3n minus 6 edges in a simple n-vertex planar graph requires 2e equals 3f, meaning that every face is a triangle. If G has some face that is not a triangle, then we can add an edge between non-adjacent vertices on the boundary of this face to obtain a larger plane graph. Hence, the simple plane graphs with 3n minus 6 edges, the triangulations, and the maximal plane graphs are all the same family. A maximal plane graph has exactly 3n minus 6 edges. Thanks for watching this video. See you next time.